Welcome to chapter 17. We are zooming right along. We've only got 3 more chapters after this one. And one of those chapters, chapter 19, will be introduced by my friend Melissa Davis. So you've really got, after this one, only 2 more with me. The end is near and the final exam is near. And I appreciate all the work you've done so far in the semester. And it looks like everyone is doing well in the class. So I'm happy with that right now. So that's not always the case, but this time it has been. So I appreciate that very much. Let me go to our sharing of the screens here. And let me pull this up. We're going to look at chapter 17, Moisture, Clouds, and Precipitation, which is what you see in the background here as I'm sitting in front of a cloud cover. This was a cloud that hovered over a neighborhood in Reykjavik, Iceland. Hey, always Iceland, yes. This was a view from my hotel room a couple of years ago. And this was a nice, bright, sunny day, except for this one cloud that was hovering around. And clouds do funky things, and we'll sort of see some of that in our lecture today. Clouds are, of course, water, H2O. We have 3 states of matter. There's actually a 4th that we can talk about, but it never happens in terms of precipitation. Solid, liquid, and gas. If you get a high enough energy, you also get plasma. That's on the sun. We won't worry about that here. Water is at what we call the triple point here in our normal environment, which means it can be in the air as water vapor, it can be liquid in your glass, and it can be solid in your glass as ice cubes or snow. Water is the only thing that naturally exists on Earth in all 3 states. And the way we go from one to the other is we either absorb heat, and that is when it goes from solid to liquid to gas, things melt, or energy is released. That's when it solidifies, it freezes. The water condenses from a gas to a liquid, or from liquid to solid. So we get rain, we get snow, we get hail, we get all sorts of different kinds of things that happen. And we can get hail in the summer. That's because, remember, up in the upper atmosphere, it's cold. So things can actually freeze there, even if on the ground it's 70, 80, 90 degrees along the way. We measure heat in terms of calories. You're probably used to that in terms of food substances. We have something that is called latent heat, which is sort of stored. This is something that is not really regarding the sort of temperature changes, but it does affect our atmospheric processes as we go along. We'll see how that happens, because we have within the atmosphere evaporation and condensation happening on a regular basis. We have liquid changing to gas. We have that's going to be evaporation. We have the gas changing to liquid. That's rain, and also misty kinds of things can be that. We call that the latent heat, as either the heat is being added or taken away from the substance. It's taken away from it when it goes from gas to liquid. It is absorbed when it goes from liquid to gas. Just like if you boiled water, you're adding energy to it. We then also have the melting and freezing process, which is solid to a liquid or liquid to a solid. Again, we release the heat when we are solidifying things. You're taking the heat out when you put things in the freezer and they freeze. You're adding heat if you melt something. Even if you just sort of sit your ice cream out and let it melt, it's absorbing the heat from the atmosphere. Notice we have a different amount of heat, 80 calories per gram to go from solid to liquid, but it takes 600 calories per gram to go from liquid to gas. So it takes a lot more to evaporate than it does to simply melt. Sometimes we'll have something called sublimation, which means we go from solid to gas. And sometimes we have deposition or depositing, and that's where it goes from gas to solid. And it doesn't go through an intermediate stage. That's rare. It happens more in human-made processes like a freezer than it does in nature, although it can happen in nature as well. And that's where we get the 680, which is equivalent to what we just saw, 80 calories here for the melting process and 600 for the evaporation process. That adds up because this is the same thing, we're just taking both steps at the same time. When we are dealing with this kind of stuff, this shows what happens there: sublimation, solid to a gas directly, deposition, gas to a solid directly. But usually we have it going from solid to liquid to gas and back through liquid to solid again. That's the more normal processes that we have. But it's always H2O. You're adding energy here, so of course the gas particles are moving quite a bit. You're taking energy away, so they slow down and then they crystallize. Remember, ice can be a crystal. So we have a strong structure that's in there. Humidity is how much water is in the air. We say water vapor there. If it's 100%, then it's raining or snowing. Saturation is when it's completely filled, and the warmer the air is, the more it can hold in terms of water, in terms of H2O. So that's why you'll often get muggy and more humid days when it's hotter, especially here in Indiana. Our vapor pressure is part of the total atmospheric pressure. Remember, we've got the atmosphere pushing down on us, our barometric pressure. We can do different ways to measure humidity. We have our mixing ratio, where we're sort of comparing the amount of water vapor compared to the remaining mass of dry air, or we can talk about relative humidity. And this is the actual water vapor compared to what it would be for saturation. That's often what we hear when we're listening to weather reports, where it says 20% or 40% or something like that. That's going to be typically the relative humidity. And that's affected by both changing moisture or temperature. The temperature going up and down, even if the amount of water vapor is in there, will change the ratio. Or you can just add more water particles, H2O particles, that will also change it there. So when we're sort of doing different kinds of assessments, in a perfect world, we might have time to do this kind of experiment in class, where we would have in our sort of test tube or beaker different amounts of water, and we would add different kinds of effects, either temperature or a kind of sort of assessment of the evaporation that's taking place there. And evaporation can take quite some time. So if you thought those experiments where we were doing things with the heat on the dry sand and the water and other things took a lot of time, these are ones that you sort of set up and leave for half an hour to an hour and then come back and check on them along the way. This sort of shows the relative humidity, how that varies with our temperature. Here we can sort of see our temperatures are changing down here. Our absolute one here, or one of the things that we're sort of seeing, we're adding more water vapor into the atmosphere at a constant temperature. So when we're looking at a typical spring day, whether it's here in Indiana or when we're thinking about it in most of the mid-section of the United States, we're going to get our lowest temperatures in the morning. We're going to get our highest temperatures in the late afternoon. We'll often have our highest relative humidity in the morning. That's why when you wake up quite frequently, you're going to have dew or fog or mist or something like that, that as the temperature goes up, that burns away. You may, in fact, still have as much moisture in the air, but the temperature has changed, so the relative humidity has gone down as a result. And then we have what's called the dew point temperature, which is when you get fog or dew or other kinds of things. You walk out in the morning and it looks like a clear day, but your car is covered with water. How did that happen? That's because the air got down to a temperature where the amount of moisture, the amount of water vapor in it, was right at the saturation point, and things began to condense on certain surfaces. You may notice that your car has condensation on it, but your sidewalk may not. Or plants may have condensation on it, but and your patio furniture may have condensation, but different things around don't seem to have it. Different surfaces will have different temperatures and be affected in this way too. When we're looking at the different dew points, say in the early fall, we can see over here in the west, that point comes at a really low temperature, whereas over here in the southern states or in the Midwestern states, it's relatively higher along the way. Of course, this is a very arid territory over here in the west, Nevada, Arizona, New Mexico, Utah in particular. Colorado, this sort of juts up into the Rocky Mountains here. So that's going to be a much lower temperature for the dew point. When we have our different ways of measuring humidity, we can use a psychrometer or a psychrometer. Either way, I've heard people I respect pronounce it both ways. And this will use multiple thermometers to give us the difference that's there. And then we have the electrohygrometer or hygrometer. Again, people I know pronounce it both ways. And this looks at how much the air can hold with an electrical charge. So there's more than one way to measure this in terms of our technology. This is perhaps the easiest way to do it is we have our wet bulb and our dry bulb, and we're sort of comparing the 2 points so that we can get to the dew point that's there. When we're looking at different kinds of ways of assessing how clouds are going to form, because clouds form from the moisture that's in the air, we have what's called the adiabatic rate. And the adiabatic rate is air compressing or expanding due to the motions of the air. But typically, we're not going to have a change in the heat energy. So it's constant over time, but things are moving. And when we have dry adiabatic rates, one of the things that we'll see is as we're going up in our altitude above the sky, or above the ground into the sky, we're going to have a cooling effect the higher we go. That's why mountaintops all have, as we've talked about before, snow-capped peaks above certain levels. Then we also have the wet adiabatic rates, and that is where the rising air cools and condenses. That lets go of the heat, because of course it's going from a gas to a more of a liquid state. I mean, it's weird to think of clouds as being liquid floating around up there, but in fact, that is what's happening in this process. If there's enough of it, it then falls due to gravity, and it rains down on us. But as we're sort of looking at what's happening here, our temperature goes down and down and down as we go up in height. This is 1,000 meters, so you might think of that as roughly 1,000 yards. But 2,000 yards were more than a mile up. 3,000 yards we're going to be 9,000 feet. So that means we're going to be almost 2 miles up at this point here. So quite a ways up, much taller than skyscrapers in New York, say, for example. So although you can get, and if you go to Chicago or New York, go to the top of the Sears Tower, or the tower formerly known as Sears, or the John Hancock Center, and you can sometimes be in the cloud, or even at the old Sears Tower, you can be above the clouds. You look out and you sort of see that there are antennae, but you don't see the rest of the city, and it's weird. But that's because this level will change depending upon temperature and depending upon how much moisture is in the air. So we have different processes that work. We have orographic lifting, and this is where we have different kinds of terrains that will act as barriers as things are moving through. It hits mountains, it hits plateaus, it hits different things then we can end up with deserts on one side because the stuff is being blocked. Then we have sort of frontal lifting, and this is where we end up with cool air and warm air hitting each other. That will often end up in, especially here in the Midwest, with tornado weather. So when we have our sort of orographic lifting here, one of the things we see is on this side, as the wind is coming, say, off the Pacific, we are being hit by the mountains. On the far side, we call that the rain shadow. Not a lot of the moisture is making it past there, so we end up with dry desert-like conditions. But on the other side, where all the moisture is being contained and retained and then raining back down, we get often rainforest kind of environments there. This is what we experience here in Indiana quite a lot: warm air which rises, cold air which goes down. But when the two fronts hit right at the edge there, we get a lot of condensation and precipitation that happens, as well as other energy exchanges that will give us our fun electrical storms. So make sure you have your surge protectors at home. Does anyone do surge protectors anymore? That used to be a really big thing. Now almost all electrical devices seem to have that built in. Then we have convergences and localized convective lifting. Here's an example of convergences. What is happening is we have different motions based on the Atlantic on one side and the Gulf of Mexico on the other that are sort of converging towards the center there. So we end up with a rather unique weather pattern for Florida that doesn't apply in most of the rest of the states because they're not a peninsular kind of weather. So this is a convergence, and you can sort of see the outline of Florida with all the clouds that are here. And then we also have our localized convective, which that's what's happening in my picture behind, is there's just this sort of one cloud. Why is there the one cloud there? What's happening to do that? Well, the sun is heating up a particular place that's letting the moisture rise, but as it rises to a certain level, and you can see those clouds are not too tall, they're not too high in the sky, because it's Iceland, it's cold already on the ground. You can see the snows on the ground there. So this was a winter time picture that I took. But the sun melted and evaporated some of the ice and snow on the ground, and it came up, and then it condensed at a certain level. The sun was still shining below it. You can sort of see how this isn't blocking much of the sun at all there. So it's still feeding the cloud along the way. When we're looking at what's happening in the sky, we're looking for air currents and different kinds of movements. We often will call that displacement. And stable areas will resist that kind of moving. But often what will happen is that will become a sinking kind of area. You might see low pressure and high pressure cells on weather maps. And Melissa's going to talk more about that in chapter 19. So I'm going to sort of leave that for her. But if we were looking at sort of an area of what we might consider to be absolute stability, we would have our warmer air and our cooler air sort of in sync with each other. And it would continue up to a certain condensation level. This can, again, change depending upon actual temperatures as well as the amount of moisture in the air. Then we have absolute instability, and this is where we have sort of areas or pockets of air that will rise or sink around the rest of it. So warmer air, if you have a warmer air pocket, it's going to rise in the midst of the rest. If it's warmer, it's going to be less dense, so it's going to be pushing things out. The warmer it is, the warmer the air is, the more the particles move, the more they push out. The cooler it is, the less they move and the denser they become, until they get cold enough and they completely change to liquid or to snow. Then they're getting less and less and less dense all the time. So if we sort of look at this kind of thing, we are ending up with sort of hot and cold on top of each other. This is sort of a normal, non-weathery kind of situation where you're still going to get clouds developing in cloud cover. Then we have conditional instability, where we're going to have different amounts of air with different amounts of humidity, or some areas will have more saturation and most of the air around it will be unsaturated. And then we have different types of clouds that will develop depending upon which kind of stability or instability there is. So here we have a sort of a conditional instability. I'm not going to worry too much about explaining all of this because, again, Melissa is going to talk a little bit about it in chapter 19. But the basics are you're sort of getting the broad strokes of how clouds form. Condensation can form into dew or fog or clouds. Water vapor typically needs some kind of surface to condense, and as we mentioned before, grass and car windows, what's happening in the atmosphere is we have different kinds of particles in the atmosphere, dust and smoke and other kinds of things that have been wafted out of the ocean will provide the seed for condensation. We can literally seed the atmosphere. If it hasn't rained for a long, long time, but there's humidity in the atmosphere, we can actually send planes up to seed. What they're doing is they're putting particles into the atmosphere that the water vapor can condense around, and it will generate clouds and rain. Clouds are made up of lots and lots and lots of minute, that's not minute, that's minute water droplets and tiny, tiny crystals of ice, like microscopic crystals of ice. And that's why, even though the crystals of ice will be solid, they're small enough to be floating, just like snow is solid, but it can be blown around. And the same is true for the water droplets. So the clouds are liquid and solid, but they're still floating up there. We have different classifications for clouds. We have our cirrus clouds, which are the highest, our cumulus clouds, which are the big sort of globular kinds of clouds, the sort of the white puffy clouds that are there on a nice day. It's like, oh, well, let's see what the clouds are looking like today. Well, I see a bunny rabbit in that one. And it's sort of a Rorschach test of clouds. That's usually what we do with cumulus clouds. And then the stratus clouds tend to be when we've got like lots of layers that cover the entire sky. And often they'll look sort of feathery in different ways. Highest clouds can be 3, 4, 5 miles up, and we're going to have cirrus and cirrostratus and cirrocumulus clouds. Notice cirrus and cirro, that's always in there. Then our middle clouds, which are 1/2 mile to 2 miles up, are going to be our altostratus. We're still getting into the stratosphere here. And cumulus, the big puffy clouds. And then our lower clouds will be just sort of regular stratus, stratocumulus, nimbostratus, which means rainy. Nimbus means rainy. Chances are good, Melissa in her discussion will tell you that her cats are named after clouds, and one of them is named Nimbus, which is that. These tend to be lower clouds, so they're about 1/2 mile to 2/3 of a mile up, maybe as much as a mile. But they can grow very tall. This is a cumulonimbus. We just learned that nimbus means rain, so this can be a rain cloud. This goes from relatively near the surface, all the way up for as much as a couple of miles. It goes way, way up there. These will often produce thunderstorms. And here we can sort of see the different types of clouds. We have our stratus, our sort of feathery, puffy ones that cover the sky. We have our stratocumulus, which are more distinct strips. Nimbostratus are the sort of the dark ones that rain, but they're not. They tend to just be rain. You know, some days you have just rain, and some days you have big, violent thunderstorms. The nimbostratus ones are the days where you just have rain. It's the cumulonimbus ones, the giant clouds over here, where you get the real big developments of our storms. And then, of course, the higher you go, alto and cirro up here. And our cirrus clouds are really the highest of the high wispy ones, way, way up there. And they can turn into globular things. That's what our cumulus means. So you're putting things together in terms of stratus, 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 as you notice here, cumulus, 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 as you notice here, nimbo, nimbus here. So we can use those parts of the words to form which ones we're getting. Fog is basically a cloud on the ground. So if you're driving through fog, you're driving through a cloud, just like a plane up in the atmosphere would be going through clouds. That's what you're doing here. Most fog happens because of the cooler surface and the condensation of things that are happening at the bottom. There are different types of fog. We have radiation fog, when the Earth's surface cools rapidly as we're sort of turning away from the sun, and we're not getting as much energy from the sun anymore. Into the nighttime, we're not getting any energy from the sun there. And typically, if there's no cloud cover, we might end up with a little bit of fog on the surface as things are happening. Advection fog is usually a warmer thing that happens in the winter. So if you have a pocket of warm air that goes across something that's frozen, you'll end up with fog there as it sort of melts and evaporates some of the atmospheric and surface water. Then we get the upslope fog. This often will happen in mountainous regions. So quite frequently in mountains and valleys, you're going to be seeing upslope fogs here. Here we can see fog rolling in to San Francisco. We have what's called the advection fog. It often will cover the entire bridge here. So that can be a little bit dangerous to drive across the Golden Gate Bridge when this is happening. And this happens quite a bit there. So it looks like clouds are taking over, but that is fog just above the surface. Now the Golden Gate Bridge is hundreds of feet high. I've gone under the Golden Gate Bridge in a cruise ship, and we were nowhere close. I mean, we're like 6, 7, 8 decks up on the cruise ship, and I was sort of in the restaurant on the back of the ship, so it was open, so we're actually watching the Golden Gate go by as we're doing this, and we were nowhere close. I couldn't like reach up and slap the bottom of the bridge. It is very high. Evaporation fogs, again, steam or a frontal fog, which is precipitation that is not fully raining down. Here we can see where fog tends to be or not. We have a lot of fog over here. These are rainforests, especially in Washington State and lower British Columbia. And we have a lot of fog in the Appalachian Mountains, and we have Appalachian Mountains up here as well. So lots of fog. Those will be those upslope fogs, those valley fogs. These will be fogs due to advection, quite frequently coming off of the ocean. Not a lot of fog, as you can see in the Midwest. We get the occasional day, hardly any in our desert areas in the Southwest. So precipitation forms as cloud droplets form, very, very tiny. You could pinch your fingers together and there would still be a little bit of space between them, and that's how small these things are. We have what's called the Bergeron process, where the temperature in the cloud is below freezing. Ice crystals will collect and then larger, and they'll grow larger till the snowflakes form and begin to fall. So we've got these sort of cloud droplets that are forming, but we have an ice crystal that will then pick up more and more of the particles of H2O. Then we have our collision coalescence process with warm clouds, condensation that's taking place in there. Large droplets will form, but they're not cold enough to freeze. So this is where we're going to get rain. Very common in rainforests, very common. And you end up with big raindrops because they'll often collide with each other as they're coming down. And so they add heft to them. So you can actually get really pelted with rain. If you've ever been out in a rainstorm where it sort of almost hurts, that's sort of what's happening. We have the collision coalescence process that's there. And then we have just basic rain and drizzle and mist, which is ever smaller amounts, or ever smaller sizes of what's coming down at you. Mist, you can't really even sense it. It's sort of there, but almost not there. Whereas rain, you can tell is there. If you can't even feel it at all, then we call it fog rather than mist. So that's one of the differences that's there. And then of course, snow are ice crystals. Sometimes you'll have several of them interlocking with each other. Sometimes you may be sort of used to here in Indiana getting these sort of almost hand-size snowflakes that sort of fall down. It's like, wow, that's a big snowflake. And then at other times that they seem to be tiny. So that happens. We get sleet, where the rain is freezing as it falls, so you're actually getting ice pellets that are hitting you. And then we have freezing rain, where as it comes down, it's super cooled, and that you get things coated. Your car is coated with ice, and then you have to sort of chip away at it along the way. And we call that glazing or freezing rain. So here we have the different ways in which this can happen. Snow, if it's sort of cold all the way down, no melting occurs. If we have a pocket of warm air, the snow can melt into raindrops, but then they'll refreeze into ice. This is where we sort of get sleet and sometimes our glazing kinds of icy stuff. And the more warm air, ironically, the more warm air it goes through, the more likely it is to turn into that freezing rain. And if we've got warmth all the way down to the bottom, we're going to have rain. But it starts out quite frequently, even in the summer up there, as snow. Then we get hail. Hail is when we have large cumulonimbus clouds. You're not going to get this with the sort of the feathery kinds of clouds. But what's happening there is we're going to have up and down drafts. So as things are falling, they're going to be shoved back up and collect more and more particles until they become sometimes even the size of golf balls or even heavier stuff. And they end up doing some good amount of damage when they come down. And here we have an example of a big splat from a hailstone. We can have small, we can have large, we can have a mix. The ideal, of course, is that they'll melt before they get to the bottom and smash through your windshield. Then we have something that's called rime. And this is where fog or cloud droplets, remember if we're in fog, we're on clouds on the ground, will freeze onto things. Notice that it always looks really lovely, but it can be damaging, very damaging to plants. And not so good for animals either. You don't want to wake up with a beard like this. But this is sort of what happens. It happens rather rapidly when there's a temperature shift that happens. Rain, easiest to measure. We just sort of collect it, usually using a funnel or some kind of bucket, and we measure it in centimeters or inches. So we have 2 inches per hour or something like that. Along the way. So we do have standard gauges that we try to use to mitigate the effects of either wind or that an area might collect more water because it's pooling up or something like that. But this is one of the things that we will try to use to assess how much rain is coming down. Snow can be either how much it would be if it were rain, or how deep it is. We had 6 inches of snow or 2 feet of snow or something like that. That's usually the way we're doing it. But the general ratio is 1 inch of rain would end up being as much as 10 inches of snow, although that can vary. And then we use radar, and you'll see that a lot in weather reports, where they'll talk about the radar measurements that they're taking inside of clouds. And that's where we get our Doppler shift, because Doppler tells you if things are going towards you and things that are moving away from you. And things that are going towards you get a blue shift, things that are going away from you get a red shift. And we can assess the way things are moving inside of clouds to tell whether or not it's likely to be a heavy or a light precipitation. And I have people outside of my window here screaming. You might hear that. So we were not having any rain or precipitation tonight, so they're all out in force. But that is chapter 17. And I will be doing lectures, video lectures for you on 18 and 20, and Melissa will be doing one on 19 for you. And I look forward to seeing you again in class.